Welcome to The Explainer. Today, we're going to talk about the thing that powers pretty much all of modern AI. You know, the chatbots, the image generators, all of it. We're talking about the transformer network. Okay, so let's just start with a super simple problem. Take a look at these two sentences. The word bank means two completely different things, right? One's a riverbank, the other's a money bank. For you and me, that's obvious. But for a machine, yeah, that's a whole different story. You know, before 2017, this was a huge challenge. The way older AI models worked, they'd give every single word just one fixed meaning, a one-size-fits-all definition. So its idea of bank would be this kind of useless, muddy average of all its possible meanings. Not very helpful, right? So the big breakthrough really came from flipping the script. Instead of that rigid, single definition, what if a word's meaning could actually change based on the words around it? What if meaning wasn't fixed at all, but was totally fluid, totally dependent on context? And that right there is the absolute heart of a transformer. It doesn't just see a word, it sees a word in its context. It creates this kind of numerical fingerprint for the word, called a contextualized embedding. And because of that, it can give bank a totally different identity in each of our sentences. Game changer. And you know what's wild? The core idea behind this is actually pretty simple. To figure out this new contextual meaning, the transformer basically just calculates a weighted average. Yeah, a weighted average of that word and all the words around it. So let's walk through that. When the model looks at bank of the river, it's scanning all the words, and it figures out, hey, river seems pretty important for understanding bank in this sentence. So it gives river a really high weight, which pulls the meaning of bank way over to its geological side. Simple as that. Okay, but how does it do that? How does the machine actually calculate those weights? I mean, how does it just know that river is the important word here and not, of or the? Well, the engine driving this whole thing is something called self-attention. It sounds fancy, but the self part just means the sentence is literally looking at itself to figure out what matters. It's this whole process of weighing how much influence every other word has on each specific word in the sentence. To really get a feel for this, let's just forget about sentences for a second. Let's try an analogy. Imagine you're in a bakery. This analogy, by the way, is inspired by the great work of Sandeep Sentwal, and it really helps make this next part click. Okay, so you walk in and you want something specific. That's your query. Let's say you're craving a bagel. Now, you look at all the labels on the display cases. Croissant, bread, muffin. Those are the keys. You're comparing your query, bagel, to all those keys to find a match. And when you find the right label, you want the actual thing behind it, right? The bagel itself. That's the value. And believe it or not, self-attention works pretty much the exact same way. All right, let's bring that back to our sentence. The word bank is our query. It then compares itself to every other word in the sentence. Those are the keys. And what happens? The model gives a high attention score to bank itself and a really high score to river. But the scores for of and the, super low. It's figured out exactly what context is most important. So here's the key takeaway. The final contextual meaning for bank is just a blend, that weighted average again, of the values of all the words. But, and this is the important part, since the weights for of and the are basically zero, the new meaning ends up being almost entirely a mix of the original bank and river. It effectively ignores the fluff. But get this, a transformer doesn't just do this once. No way. It runs this whole self-attention process multiple times, all at the same time, each one looking for something a little different. This is called multi-head attention. It's kind of like asking a panel of 8 different experts to analyze the sentence. One head might look at grammar, another at synonyms, and together they give you this really rich, multi-layered understanding. Okay, so you might be thinking, what about word order? This whole weighted average thing seems to kind of ignore it. Well, transformers have a really elegant solution. They just add a unique mathematical tag to each word that basically says, hey, I'm the first word, or I'm the second word. It's a super simple but really robust way to give the model a sense of the sequence. And unlike the old ways, it doesn't break down on super long sentences. So we've got this incredibly complex architecture, right? But that leads to the big question. How on earth does a model with millions or even billions of these parameters learn something as messy and complicated as human language completely from scratch? Well, it's basically a 2-step dance. The first step is called pre-training. This is where the model just reads a giant chunk of the internet to get a general feel for language. Step 2 is fine-tuning. That's where we take that generalist model and train it to be a specialist at one specific job, like, say, figuring out if a movie review is positive or negative.
That pre-training step is really just a massive game of fill in the blanks. The fancy term is masked language modeling. But all it means is you take billions of sentences, you randomly cover up about 15% of the words, and you make the model guess what's missing. That's its only job, guess the masked word. And by doing this a billion times, it starts to learn everything: grammar, facts about the world, even a little bit of reasoning.
So once you have that powerful pre-trained model, you can fine-tune it for almost anything. For a task like classifying movie reviews, you just need to show it a much smaller set of examples that are already labeled. The model then connects all the language patterns it already knows to the specific labels you want, like positive or negative. And this whole process is just incredibly efficient. So this whole process gives us these insanely powerful AI models that are, at the top of their game. They completely dominate the field, but they are far from perfect, and they come with some pretty significant trade-offs. Just to give you a sense of the scale we're dealing with here, look at this number: over 1 million. That's how many different knobs and dials, or parameters, can be in just one single multi-head attention layer. And a real model? It stacks dozens of these layers, leading to models with billions of parameters. It's just massive. And that brings us to the main trade-off: performance versus cost. On one hand, the understanding of context you get is absolutely state-of-the-art. But on the other hand, that self-attention thing we talked about is super expensive, computationally speaking. Think about it. Every single word has to look at every single other word. That means the longer your sentence, the processing time just explodes. It makes these models kind of slow and really, really hungry for powerful computers. Now, of course, researchers know all about these problems, and there's this constant race to make transformers better, faster, and smarter. People are working on all kinds of clever solutions, like building more efficient attention mechanisms that don't slow down so much, or distilling these giant models into smaller, quicker versions that can still do most of the work, and even finding clever ways to handle word order. So it's pretty amazing when you think about it. We started with what seems like such a simple problem, right? Just figuring out the two meanings of the word bank. And from that one little problem, this core architecture, all built on context and attention, has gone on to completely reshape the entire world of AI. It's unlocked things we're really only just starting to figure out. And that leaves us with one final thought. We started this whole journey with the machine just trying to understand a single word in a sentence. Now they can understand the context of huge documents, of images, even sound. So now that machines can truly grasp context, what's next? What's the next great frontier for their understanding?